Hi, everyone. Thanks for joining. You're here because you're developing a high-performance multi-region application, and you're looking for the right database to store your data. I'm excited to share that yesterday we announced the general availability of Amazon MemoryDB multi-region. In this session, we will show you how Amazon MemoryDB multi-region can help you build a multi-region application. We'll dive deep into the underlying technology behind it, and we'll talk about key considerations you have when choosing a multi-region database. My name is Itai. I'm the General Manager of In-Memory Databases. With me is John, the Head of Engineering for MemoryDB. Before we start, please raise your hand if you're building a multi-region application. Cool, a lot of hands. Cool. So we will show you how MemoryDB multi-region can help you build a high-performance, large-scale multi-region application with 5 nines of availability. AWS has 108 availability zones across 34 regions, and more regions are coming. And every AWS region consists of multiple availability zones built for high availability and resilience. And each availability zone has one or more discrete data centers with redundant power, networking, and connectivity. And the availability zones are physically separated by a meaningful distance. So the question is, why do customers like you need to build multi-region applications? These are the two main reasons customers tell us that they need multi-region applications. The first reason is to increase resilience in the unlikely event of major disruption in a single region. This could be disruptions in the region. This could be disruptions in the networking or connectivity to the regions. And these customers, they have critical applications, and they cannot tolerate such a risk, even though it has low probability. And some of our customers have regulations that they need to adhere to. For example, some of our customers in the health industry or in the financial industry, they have to run certain workloads in multiple regions for compliance reasons. The second reason is companies that have global businesses, and they need to build their applications in multiple regions in order to provide low latency and a great customer experience for their own customers. Think about global applications like gaming or retail, where you have global data like leaderboards or user sessions. For example, a global company that has a customer in the US, this customer can travel to Singapore, and they would like to continue to using the app or the website. And the cross-region latencies between these two regions is very high. It's hundreds of milliseconds. And without a multi-region application, what will happen is that the customer will have high latency and a bad customer experience. Okay, so we need multi-region applications. Why do we need the data layer to be multi-region? Can't we just do cross-region calls instead? So in the case of increased resilience, you need the data for disaster recovery. And even a standby region needs the data because you will not have business continuity without having your business data. And then in the case of global applications like gaming or retail that have the global data and they need the low latency, for example, to retrieve the customer session or to update the leaderboard, they need the low latency. And the typical in-region latencies are sub-milliseconds, where the typical cross-region latencies are dozens or hundreds of milliseconds. And if your application does multiple sequential calls to get the data, that means that you will have a very high latency, and it will impact the customer experience if you don't have the data locally. For a multi-region data layer, you can build your own custom solution and replicate data across regions or copy snapshots or maybe use some third-party solutions. But as you will see throughout the session, there are some hard problems to solve, like correctness, consistency, availability, and performance. So alternatively, you can use a multi-region database that already solves these problems. And we will show you later in the session how we solved some of these problems with MemoryDB. So which multi-region database should you choose? In the next few slides, I will show you what considerations you have when choosing a multi-region database. So first, let's cover consistency and durability. Think about your recovery point objective, your RPO. What is the maximum data loss that you can tolerate in the unlikely event of a region failure? And this leads to the next question, synchronous or asynchronous cross-region replication. So let's see how synchronous cross-region replication works. The client will do a write request to the database in the local region, and a write request could be either an insert or an update if it's a relational database, or it could be a set key value if it's a key value database like MemoryDB. Then the data is being replicated synchronously to the other region. It will be followed by an ACK, and then eventually you will get an ACK. And the key idea here is that there's more than one way to do this, and there are algorithms like two-phase commits and others. But the key idea here is that the client will receive an ACK only after the data is durable in both regions. And this is where you get strong consistency, because you know that you get the ACK after the data is durable and consistent in both regions. Let's see how asynchronous replication works. As before, the client will do a write request in a local region. But this time, the client receives an ACK after the data is durable in a single region. And then the data is replicated asynchronously to the other region. So even if there is a problem with the replication, if there's a failure in the replication, since the data is durable in one region and the client received an ACK, then it is considered as durable. In such failures, the database will retry later, and the database will retry later. This is why asynchronous replication have eventual consistency. In some point in time, the data will eventually be consistent in both regions. So let's compare the pros and cons of each one. The main advantage of synchronous replication is that you can achieve RPO 0. And we hear some customers asking for this kind of consistency. However, the major downside here is that a lot of customers don't need this RPO 0, and they cannot tolerate the high write latencies. With asynchronous replication, it is the opposite. The main downside is that RPO 0 is not possible, but the write latencies are substantially better, within the order of a few milliseconds. And usually the replication lag is also a few seconds, and many customers prefer the low write latencies over the 0 RPO. We see it's very common to see asynchronous replication, solutions like DynamoDB Global Tables, Aurora Global Database, Elasticache Global Data Store, and now MemoryDB Multi-Region. They all have asynchronous cross-region replication. The next consideration is high availability. And as we discussed earlier, one of the two primary reasons that customers build multi-region applications is to have higher availability and business continuity in the case of a region failure. So the next question you want to ask yourself is, what is your recovery time objective, your RTO? What is the maximum downtime that you can tolerate until you are able to restore your operations? This leads to the next question. Should you choose a multi-region database that has active-active or active-passive. So with active-passive cross-region replication, the data is only written in one region. You have a single writer, and then it's been replicated to the other regions. With active-active, the application writes simultaneously in multiple regions, and you have multiple writers. There is a two-way replication between the regions, and the database needs to resolve the conflicts if there are any conflicts. And please note that the decision whether to use active-active versus active-passive is orthogonal to the decision whether to use synchronous or asynchronous replication. These are decoupled decisions. The main advantage of active-passive is that it is easier to build and has fewer constraints and limitations. For example, with active-active, you might not be able to fill your entire capacity in one region because the database needs to reserve capacity for writes in other regions. Similarly, with active-active, you have multiple writers, and therefore there could be write conflicts. So the database needs to resolve these conflicts, and you need to understand what to expect in the application. However, the major downside of active-passive is the lower availability. In case of a region failure, which is why so many customers use multi-region applications in the first place, you need to manage the disaster recovery if you have active-passive. You need to detect the region failure, and you need to do failover in the application side, either manually or automatically. And you need to failover the software stack to the other region. And in practice, it is very hard to do and very hard to automate. And it's also error-prone, and typically it takes several minutes, if not much longer, to do a region failover. And that's impacting your recovery time objective. This is why so many customers prefer active-active. With active-active, managing the region failure on the application side is much easier because you don't need to do a database failover. The application continues to read and write in all the regions at the same time, and near RTO 0 is possible. All right, so we talked about synchronous versus asynchronous. We talked about active-passive versus active-active. Another consideration is the number of regions that the single database can support. For disaster recovery, typically 2 regions are sufficient, but for global applications with global data, they typically need the data to be available in all of the regions, and therefore the database needs to support multiple regions. Similar to other use cases that you're familiar with, you care about other considerations across security, compliance, the data layer API, the ease of use, scalability, and performance. So which database should you use for your multi-region application? AWS provides a wide range of purpose-built databases built to meet modern application demands. And with the explosion of cloud-native applications that require different access patterns, data models, performance, and scale, you can choose from a solid portfolio of purpose-built databases that fit your application needs. Some of our databases offer multi-region, cross-region replication. So today we will focus on MemoryDB. Before we talk about MemoryDB multi-region, we'll do a short overview of MemoryDB. So what is Amazon MemoryDB? It is the fastest durable database that AWS offers today, with microseconds read latencies and low single-digit millisecond write latencies. A single node can support up to 450,000 read requests per second and 100,000 write requests per second. It has a memory-first architecture. So all of the data is in memory, and the durability is achieved by a transactional log. So that's how you get the very low latencies and the high performance. MemoryDB is Valkey and Redis open source compatible. And before we move forward talking about MemoryDB, please raise your hand if you're familiar with Valkey. All right, great to see a few hands. Please raise your hand if you're familiar with Redis. Okay, everyone here is familiar with Redis, or almost everyone. So I kind of expected this answer. So before we move forward with MemoryDB, let me introduce Valkey just for 2 slides, a couple of minutes, so you have context for the rest of this session. In March this year, Redis announced that future versions of Redis will no longer be under the open source license. Almost immediately, the community of avid developers forked the project and created Valkey. It is developed by some of the same people who previously developed Redis before the license change. And some of the previous Redis maintainers became Valkey maintainers, and many developers in the community joined the effort. Besides the large community of contributors, it is supported by over 40 different corporates, including large cloud providers. It is hosted by the Linux Foundation, so it is vendor neutral and it stays open source forever. And the first version of Valkey is also a fork of the last open source version of Redis, which is 7.2, and it is fully compatible with it. And this is also the first version that we released, our managed services, Elasticache and MemoryDB. We launched Valkey on both of our managed services with substantial lower prices. Both services provide an online upgrade in just a few clicks, so you can have a simple drop-in replacement. And we launched MemoryDB multi-region with MemoryDB version 7.3 for Valkey. And these lower prices make MemoryDB multi-region even more attractive to you. All right, so now let's go back to MemoryDB. So we talked about Valkey and Redis open source. So it is Valkey and Redis open source compatible. And you get the rich data structures and APIs like lists and sets and hashes and sorted sets. And you benefit from the popular Valkey and Redis open source ecosystem. And you can use client libraries in over 50 programming languages. And you essentially get the rich functionality of Valkey with durability. MemoryDB is designed for zero data loss. And one of the main innovations that we built in MemoryDB is a multi-availability zone transactional log. Every write is acknowledged after being written to at least 3 different copies in at least 2 different availability zones. And it leverages the same underlying technology that is used by S3 and by Amazon.com ordering data. In the next few slides, I will show you how MemoryDB achieves its durability. And similar to other AWS databases, it is fully managed. It has high availability with 4 nines of SLA and other important traits across security, compliance, and scalability. Under the hood, let's see how MemoryDB achieves its durability and high availability in a single region, and later we will show how we do this in a multi-region. So here is a MemoryDB cluster. In fact, it's one shard out of many in a MemoryDB cluster, and it will have one primary node and 1 or more replicas. It will have the multi-AZ transactional log, and when there is a write request, the client will send the write to the primary node. The primary node will go write the data in the transactional log. The transactional log will go replicate the data across at least 3 different copies and 2 different availability zones. And then it will return an ACK to the primary node, which will return an ACK to the client. At this point, the client knows that the data is durable. Asynchronously, the data is replicated to the replicas, and you need this for high availability. So let's see what happens if there's a failure. So again, the client writes request to the primary node writes the data to the transactional log, and then after it's been replicated in the transactional log, it returns an ACK to the primary, which returns an ACK to the client. Now let's see that the primary node fails. What will happen is that the data will go and be replicated to the replicas. And here is why we favor durability over availability. We want to make sure that the replica, before it's promoted to a primary, it has all of the data. And only after the replica fully catches up with the replication log and all of the data that exists in the transactional log, only then it is being promoted to a primary. And this is how we assure that there is no data loss. And typically this takes less than a second, and because we continuously replicate data to the replicas. After the new primary is promoted, the client is being redirected to the new primary and sends the IO to the new primary. As we said before, the data will continue to be replicated asynchronously to the replicas. So in case there's another failure, we can do the failover fast, and catching up from the transaction log will be fast. All right, so this is how we provide fast failover without losing data. We see customers using MemoryDB for many different workloads across different industries. And some of the common use cases include microservices, data stores, session stores, leaderboards, and message queues. And customers benefit from MemoryDB data structures, the low latencies, and scalability. So let's move to the second part of this session. So as I said when we started, I'm excited to share that yesterday we launched the general availability of Amazon MemoryDB multi-region. Amazon MemoryDB multi-region is an active asynchronous cross-region replication database. It is designed for 11 nines of durability. It has 5 nines of availability SLA and has enterprise-grade security and compliance. It has microseconds local reads and low single-digit millisecond local writes. It has the open source API of Valky, and it can scale up to 500 nodes in a single cluster in every region. And please note that this is not just a list of bullet points. These are specific design and product choices. Based on our discussions with customers, we learned that they prioritize high availability and low latencies over strong consistency across regions. So we decided to build a multi-region, active, asynchronous multi-region database. And it has the pros and cons that we talked about earlier when you consider building a multi-region database. So now I will hand it off to Jean to talk about these things and dive deep there on MemoryDB multi-region.
Thanks, Itai. So let's take a look at the MemoryDB multi-region architecture. And the best way to do this is to take a deep dive and add a data flow between regions. So let's pick an example with a 3-region cluster with one member in US West 2, another one in US East 1, another one in US East 2. We'll start by setting a command, like sending a set command, which is a Valky command to set the value yellow to the key sun. As Ita mentioned earlier, the data will be written into memory, then sent to the transactional log. Once it's replicated across multiple availability zones, we receive the ACK back, and then we can send the ACK back to the client. MemoryDB multi-region replication is asynchronous. What that means is we don't wait for the ACK to be sent all the way back to the client before we start replicating. So the replications will happen asynchronously. The multi-Z transactional log is essential to the way we achieve multi-region replication. So each region will pull data from the other region's transactional log and apply them locally. To ensure durability, we won't return the ACK back. So now that the data has been replicated across regions, let's take a look at another example. So this is the key set the key back with the value read. It's written to the transactional log, then we send the ACK back. And then we send the ACK back to the client. Similarly, because replication is asynchronous and we are active-active, we're able to write to the other region. There is no role like a region is a primary, another one is a secondary, both, and it's read-only. All the regions are active-active. Then we replicate the data between regions. And this is happening asynchronously in the background. We don't wait for the data to be replicated before we send the ACK back to the client. Here, you probably noticed that the replication is bidirectional. It's happening across all the regions. What that means is US East 1 will be reading data from US West 2, and US West 2 will be reading data from US East 1. So when a write happens in US East 1, it'll be written back to the transactional log in US West 2. But also, it means that US West 2 will end up seeing its own write into US East 1 transactional log, because everything happens in all the regions at once. Thankfully, we can use the key feature of our multi-AZ transactional log to filter data that we read back and we apply locally. This avoids replication loops, but also save on data transfer cost across region. And because we active-active, we can send the same data across the third region, where we send another key, and then the key is written back with the value to the transactional log, and it gets replicated back to the other region asynchronously. You've noticed here that I've drawn arrows that go in the same way and at the same time. The replication is really independent from regions to region. And what that means is the regions will be independently pulling data from the transactional log, and it won't be happening exactly at the same time. We also ensure we write to every single transactional log in every region to ensure multi-region durability, so that individual region can restore their data independently in case of a failure. So far, the example we've seen, we're on different keys, but now you're probably wondering, what if we have two regions writing the same data at roughly the same time with different value? So here we have two regions, US West 2 and US West 1. They're both trying to update the same key sun with a different value. To take a look at this, we'll need to use a different view, where here we have the same architecture, but just the two regions in questions, with the first region at the top and the second region at the bottom. We'll use this view in the next few slides, so I'll spend some time to explain the different details of it. So in the square, this represents the state of your database. The curly braces means that the database starts empty at time t0. And then t1 will be a time that's in the future compared to t0. Then this is the same example that we had before, right? We had the command set on setting the value red for the key sun. That happens at t1, and shortly after, in the other region, we have the set command setting the value yellow on the key sun. We'll do replications like we've seen in the previous slides, where the first regions will read the commands from the transactional log and try to apply them locally into its own transactional log. As we do so, what we do is we compare the timestamp, the time when the command was issued versus when was the last time that key has been updated in our region. So I'll go a bit slowly. So US East 1 has the value red for the key sun. That was updated at time t1. And then when we replicate, we receive the command sun yellow that was executed at time t2. Here we see that t2 is more recent than t1, and we favor the last update. We favor newer data that have been updated. So what that means is when the regions process that data, we'll change the value red to yellow because we favor the most recent data. This technique is called last writer when. We'll process the same thing in the other region, and then we compare T2 of the key locally versus the T1 from the command that's coming from the region. And here we don't need to do anything, because T1 is older than T2, and the value we have in memory in this region is more recent, so it stays the same. And through the technique, we can get the two regions to converge eventually with the same data. To achieve last thread win, we needed to store metadata in memory in a transactional log. So let's work through an example to see which ones. So the same thing, cyan yellow. So we first need to record the timestamp when the command, the time when the command was processed, which we store in microseconds. We store that in memory. As seen earlier, we use it to do the comparison. But we also need the timestamps in the transactional log, which include the command. So in the log, we don't include the value, we include the command that represents the value. And then we also need to include the region of origin. This is useful so later on, we don't end up replicating the writes that were issued by these regions when we read the data from other regions. Because remember, this command will be read by other regions and also be made durable in their own local transactional log to ensure multi-region durability. Val key is a lot more than the key value store. The previous example was key value, but it supports a lot many more data structures like hashes, lists, set that can be sorted. Here are the two most popular data types, sorted set that we can use for leaderboard. It counts unique elements into a set, and then hash maps are key value pairs within a single key, and it's usually used for session stores. So let's see how we can make those dataset multi-region. To do this, we'll pick an example, again, with two regions, and we'll use a set as an example. So two regions will be interacting with a set object. Here we'll use the sadd command, which is the val key command to add an element to a set. So here the set is called object, and the element we want to add to the set is bag. For those complex data type, having timestamps just at the key level is not enough. Every single element within this set needs to have its own timestamps too. So we can do a second level of conflict resolution if they arise. Then at a second time, on the same object name, but in a different region, we try to add the object chair at time t2. And then in the first region, we add a second object, a second item in the set objects. So here, we have two regions they haven't replicated yet. So if I were to query the members of the set in the first region, I will get two elements. And if I were to query the members of the set in the second region, I'll get one element. But the goal here is really to end up with a set that has all the elements in both regions. So we will replicate the commands. We'll read the commands from the second region to the first regions, and then we try to apply that commands to our own memory. But here, there is really no conflict, because there is no chair member in a set called objects. So we can safely add it without creating any conflict, while keeping the timestamps for that items also for later on, if we needed to do conflict resolution within the set. Same thing, replications flows bidirectionally. So in the second region, we process both commands, and they can also both safely be updated into our own set locally, because they don't conflict with any other value in that set. So thanks to this technique, we're able to have both sets converging into both regions. So this technique is called CRDT, of conflict-free replicated data types. It allows for multiple regions to work and write on the same object, on the same key at the same time. The writes are propagated asynchronously with timestamps information. Here, in our example with MemoryDB, it's microseconds. Concurrent writes are merged in a consistent way, so all the regions, even though they'll be processing update at different times, they'll all be converging to the same value at the end. And we use last thread win to track conflicts at the key level, but also at the sub-key level. And all of this has been analyzed with formal modeling technique using the P language to ensure correctness of the algorithm that we use. So now that we've seen data being added, let's see how data can be removed across all the regions. So we start with the same data at time t0 across two regions, a key k with the value foo. Then we set the key to a new value bar at time t1, and then the second regions will delete that data. it will delete that key, and now we end up with an empty database. We'll follow the same technique where we read the command from the remote transactional log and try to apply them locally. That command was processed at time t2, and then we compare the time of the command t2 with the timestamps of that key, when that key was last updated in the first region, which is t1. T2 is newer than T1, so the correct thing to do here is just to delete that key. However, replications flow the other way too, remember? So now we process the set k bar command at time T1 coming from the other regions. Unfortunately, our database is empty. So we have no way of attaching the metadata, so the database is empty. Okay, we apply the command, and then we create that key with the value bar. However, this is a problem, right? Because now both regions will be divergent forever. So we need to fix this. And the way we fix this is we use a technique where we repropagate deleted commands we receive back to other regions. So now we actually can reprocess that command, so that way all the regions will eventually converge and get to the same data. So I get the delete command, the one that I originally sent, delete k at timestamp 2, but now my database is no longer empty, and I can reprocess that command. We call it delete repropagation, and with this technique we're able to eventually converge, and both regions have now the same data. So now that we've seen how we read and write to the cluster, let's see how we can scale a multi-region MemoryDB cluster. But before we do this, we have to look at how we scale a local MemoryDB cluster. So here in this example, we have a 3-shard cluster with 1 primary each. The small, colorful square represent data. More accurately, think of each square as a group of data items with keys and the corresponding data associated with them. In MemoryDB, each group of keys is called a slot. So each one of those squares are called slots, and it's a val key term. Each keys will be uniquely mapped to a slot, and each slot will be uniquely mapped to a shard. And then a primary and the replica within the shard will have the same data. If you get close to the cluster capacity, or you need more performance, either read throughput or write throughput, we need to scale the cluster. The first options you have is to increase the number of replica. So here we start with 1 shard, 1 primary, 1 replica. You can add a second one or a third one. This will allow you to scale the read capacity and the read throughput available for this cluster, but not how much data you can store within that cluster, or the write capacity, because that's constrained by the primary. The second options you can do to scale is to scale up the instance, or go for instance size that's bigger. So here you go from a small instance to a bigger instance. This will allow you to store more data because you have a bigger instance, but it will not increase your read capacity or your write capacity. The third and the last and the preferred options to scale is horizontal scaling, or scale out, increasing the number of shards. We can start with 1, add another one, and add a third one. This is really the preferred and the recommended options, because not only it lets you scale the capacity of the cluster because you now have more primaries, but you can also scale the read and the write capacity because you have more replicas but also more primaries. So now let's take a look how we can do horizontal scaling for MemoryDB multi-region. So we'll start with an example with 2 regions, US West 2 and US East 1. They both have 2 shards, and we want to add a third shard. Adding a shard with MemoryDB multi-region is a multi-region operations, because eventually we want all the regions to have the same topology. However, they will apply those scaling operations independently and eventually converge to a state where a topology that's similar. So we'll have to see how we handle this situation. So let's walk through adding the shard 3 in the first region. The shard is added, it's not empty, it has no slot, no data on it. So scaling works, horizontal scaling works by moving slots. So here you've noticed we copied this white slot from shard 1 to shard 3. But then because shard on the USDIS1 side, the slot white, it's still in shard 1. So we're going to be getting updates for keys on that slot in this region. So we need to, that will be received by shard 1. And then will be sent to be forwarded back to shard 3. Then we continue our scaling operations. We'll move the green slot from shard 2 to shard 3. And then once the data is in shard 3, we can enable forwarding because we'll be receiving some updates from shard 2 on the green slot as well. That needs to be sent to shard 3 now because the other regions already moved in the scaling process. And now we don't need that data onto shard 2 anymore. Now the second region proceed, remember, everything's happening at the same time. So here it looks very sequential, but really the operations are all happening at the same time. We'll start by moving the white square. Again, we want the topology to converge eventually. So the white slot moves from shard 1 to shard 3. But because the white slot is already on shard 3, I don't need to do any forwarding in this region. I can directly replicate the data and the updates from shard 3 to the other shard 3. And similarly for the green slot, we finish our scaling process by copying the last slot over and then replicating now across the two regions on shard 3. And now we finished our scaling process and both regions have the same topology. So let's wrap everything up with an example. So we'll pick a multi-region session store example. In this example, we have 2 regions and 2 applications at the bottom. They're represented by the mobile phone here. We have Bob. Bob lives on the West Coast, so naturally it will prefer connecting to the cluster on US West 2 for lower latency and better performance. So here Bob will try to create a session by logging in. We'll talk to the API gateway, it will talk to the application, and the application, like we've seen before, we write the data into MemoryDB, it goes into memory, then we send the ACK back, then we send the ACK back to the client and gets all the way to the application on the mobile phone at the bottom. Replication is asynchronous, so we don't wait for data to be replicated before we send the ACK back to Bob. Then the data is replicated, we pull the data from the log, so USDIS1 will read the command that were persisted in US West 2 transactional log, and we'll write them back, and we get the ACK back. And now the session's been replicated. Same thing, we have another user on the East Coast. That user would prefer connecting on the East Coast for better latency too. Goes through the same process, we create the session, write the key goes into the transactional log, we get the acknowledgement back, we send it back to Alice, and now Alice is logged in with the 200 good to go. Then we'll replicate the session to the other region, and now Alice's sessions has been replicated to both regions. So now let's see what happened if there were failure on the US West 2 regions. Now first we'll see Bob needs to update his session with liking a post or interact with the running session. So now Bob writes to the transactional log with the new updates, and then we get the ACK back. And then we write to the gateway, and we say, Bob, you updated your sessions. So now we can have a failure, and then the value is replicated. We get the ACK back. So now the application fails. The session's been replicated. And Bob needs to access that session data. So what we could do is Bob can now connect use this one because the data has been replicated, but also it is an active configuration. So there's no failover involved. The data is available right away. You could just go to the API gateway in that region, goes to the application. Then you can say, get me the data for Bob in that region because it's been replicated. And now you get the AG back. And then you get the data back, the thumbs up back in the application, and you can send it back to the client. So here we've seen how data has been replicated across all the regions. Data is durable across all regions. And we see how you can achieve really high availability for your application. So next, we'll see how you can get started. As Itai mentioned, super happy we launched yesterday. It's available in the console over 12 regions, up to 5 regions in a single cluster, with more regions coming soon. And this is the end of our session. I want to thank you for diving deep with us with MemoryDB active-active architecture and learn how to achieve low latency, high availability, and resiliency for your customers. Please take a few minutes to take the survey for this session and share your feedback. We use this feedback to improve our sessions over time, not just for reInvent, but also for other AWS events. Thank you.